afternoon. Welcome to BCS. Welcome to IT Now magazine and this special webinar with James Byrne from IBM about he's going to be talking about weather forecasting and climate modeling. My name is Martin Cooper. I'm a writer on IT Now magazine. I'll need to apologise for my slightly croaky voice. I won't be doing much talking. James is very much the star of the show. All I would say is if you've got any questions, please put them in the chat option in Zoom at the bottom of the screen. We'll pick those up after the presentation. So please, James, introduce yourself and take to the floor.
Thanks very much, Martin. So yeah, hi everyone. Hopefully we can see screens okay. I'm going to jump a bit around as well after my slides. I'm going to show you some weather as well and a little bit of code. I hope you don't mind that, but it won't scare you too much, I don't think. So I've been asked to talk today, and I'm assuming a relatively IT focused audience. So I thought some education on weather and climate modeling would be good, and also let me show some pictures of supercomputers, which I think everyone likes, with their flashing lights and rows of servers. So today I really want to get people sort of aware of some of the latest sort of technology developments in weather modeling and climate modeling. And like we say, any questions, put them in the chat, we'll address them afterwards. Or if you want to find me on LinkedIn, I'm relatively active there and you can reach out and I can connect with you directly there if you want to pick my brains about anything here today. So look, I work as a meteorologist, a meteorological solutions engineer with IBM. I've worked for about 20 years with weather data, a variety of roles, and started with IBM about 5 years ago. Sort of set the scene for the talk today. Weather is important. Yeah, now IBM actually bought a weather company 6 years ago, but weather impacts everyone, every business. I mean, last year, $95 billion worth of losses globally. Joint warmest year on record, according to NASA. NOAA, the National Oceanographic Administration, said it was the second warmest year. So, and they used a different statistical framework to assess that. So that already shows statistics and weather data can come very important here. But yeah, it's very important. IBM bought the weather company. They were already doing a lot of work with weather science. They had their own weather model that they were running, Deep Thunder, and then that's been incorporated with the weather company's weather modeling now. We do a lot of work with sort of atmospheric modeling, short-term modeling, but also the climate modeling side of stuff now as well is really accelerating. And IBM Research are doing some very interesting work on the climate impact modeling as well. So my role in IBM, I'd love to be a weather modeler myself. I've kind of tinkered a little bit, I suppose, over the years, but I'm more as a meteorologist to help bridge the gap between customers and the technology, the products that IBM have. And we've got a lot of customers, a lot of different types of customers, different industries. So transport companies, agriculture. I work with insurance companies who use some climatological based risk models that we have. And also they use the weather to trigger alert messages to policyholders. So you can get an email from your insurer telling you when there's going to be a hailstorm arriving to wreck your car, for example. Utility companies, so water companies use our data and dashboards. Agriculture use the data in their crop and yield models. And also sort of forecasting disease as well. So that's all based upon some of the seasonal forecasts that we've got. What else have we got on here? Airlines and pilots, of course. We've got a bespoke platform to help the aviation industry. And pilots have an iPad version of that, so they can see what's the weather doing as they're flying. And then there's lots of niche customers as well. I work with a really exciting startup that have come out of STFC in Harwell, and they're using the weather data to help optimize satellite data transmission. So satellite data transmission, when it rains, it attenuates the signal transmission, and they're using our weather data to help improve and optimize where the base stations for satellite data transmission should be located, and and operated from. And then we have the consumers, and we have the world's most popular weather app. It's on every iPhone, and also Google and Facebook get their weather data from us as well. Or you might watch the weather on TV. So that the weather can be consumed many different ways. And actually, a lot of people probably are looking at the weather on the TV, looking at your iPhone app, you're looking at perhaps the BBC website or the Met Office in the UK. And it's that combination of different weather forecasts that is actually one of the exciting developments and one of the exciting methodologies that we use that I think is, from the IT perspective, is quite interesting. That's what we're going to dive into today. So, weather modeling. How does weather modeling work? I think I've already said I wouldn't describe myself as a weather modeler as such, but I've worked with weather model data for nearly 20 years now, and I think to do that you build up an understanding of how they work. Basically, the atmosphere is a fluid, a mixture of gas and clouds and water vapor and a few other little small particles. But that fluid follows the laws of physics, and you can relatively simply describe the movement of those of that fluid around the globe. Some equations. Don't worry, we're not going to be quizzing on these later, but I've put these up. I did learn these probably 18 years ago when I did my master's. But this is effectively the starting point of the weather model. Okay, you take a set of dynamic equations. You'll see you've got T in here. So this is basically looking at the change over time in atmospheric variables. Okay, so you build up, you have a model effectively that's saying what's the state of the atmosphere now, what will it be in a certain time ahead. Okay, and then you need to feed that model, that set of equations, with a set of observations. What is the weather doing at my point now? Now, of course, you can run that for a single point if you like. Most people for a weather model are interested in the weather for a region, and obviously to track the weather progressing through a region, you need to start with a grid. So you start with a grid of data points. I pulled this picture from NOAA. I'm sure they won't mind me using it. This is a global and a pictorial representation of a global grid, but you basically grid up the atmosphere. You have to try and, for each grid point, I mean, the models, the grid size can range. You have a grid size across the surface, and then that goes up vertically up into the atmosphere as well. Some of the best models now, you're looking at sort of up to 200 layers up into the atmosphere, and a grid point resolution of about possibly 1 kilometer or even less in some instances. When I first started forecasting, the sort of standard model we used was on a 50-kilometer grid. So you'd basically have a 50-kilometer model running, and you need to build up your observations. You need to work out what's going to be my best estimate of what the weather data is doing at that grid point, and then you use your equations to project forward. What will be the state of the atmosphere in 10 minutes, in 50 minutes, 20 minutes, and you iterate it forward. And of course, you're solving the equations each time to project forward. You're then assimilating the results, and that effectively is your forecast of the data. Okay, weather modeling. Critical inputs are the observations. Just a few moments on this chap here. This chap here is a Geordie, born in Newcastle in 1881. He's called Fry Richardson. Brilliant mathematician, physicist, and also effectively did the first numerical forecast in the early 19th century, 100 years ago. He did a forecast for a point. It was terribly wrong, but he spent weeks and weeks forecasting what the forecast for the point would be. As a result of this, he then also proposed, as he carried on researching this, he proposed this picture on the left. I mean, this actually was drawn in more recently for someone at Dublin Trinity College. Beautiful picture representing this guy's, Fry Richardson's, idea of this amphitheatre, a forecast factory, I think is the term he used, where he wanted to get what he called computers. For him, a computer was a mathematician, so effectively a processor. And he wanted to have 64,000 mathematicians sitting around an amphitheatre, all processing the equations and doing the calculations to forecast what the weather's going to be for every point on Earth. Didn't actually happen because a few years later they invented computing, and we've been working as meteorologists, working very closely with computing technology thereafter. And supercomputing obviously is it's one of the main uses of supercomputing technology, is to use that processing power to calculate the forecast. Okay, some of the problems with forecasting: we can't measure the weather everywhere, so we haven't got an exact view of what the weather is doing at every point on Earth. The equations themselves are not exact. There are issues with the physics. We've got a pretty good job of understanding how the atmosphere works, but we have various parameterization schemes which allow for certain sort of weather scenarios or certain weather things to be fitted in. Also, the equations are non-linear, so they will ultimately diverge over time, and you get chaos, and the forecast will eventually be wrong anyway. And then one of the big problems, we are overcoming this with technology, is the data. It's the scale of things, is to be able to process, store, transfer, and display the data at scale. It requires huge amounts of processing power. Okay, but of course, computing can fix that. Data assimilation and quality control. I'm going to quickly fire it here. Oops, where's my, excuse me, sorry. Oh, I think it's here. No, hang on, let me go back to my meeting. What I'm going to do is I'll bring this over here. Oh, goodness me, live demos. There we go. Excuse me for the delay here. Here's a dashboard. Right, I wanted to show some live weather. I'm a meteorologist, so this is a weather dashboard that we use with a variety of customers. And what we've got here are just some of the observations that we're pulling in around the world. So IBM have its own weather model. I'm going to come on to that later. We've got some different types of observations here. We've got I want to overlay the radar. I've got the pressure control should be on here as well. The dots are from weather observation stations. The round dots are from government observations, and these do form a key part of what we build into our weather model and the other modeling agencies around the world. We've also got on here the square dots, the square sites. These are from personal weather stations. IBM use these to give a bit of extra value to a bit of extra accuracy to our forecast as well. We've got to very carefully control personal weather stations because they're not maintained by national Met services, so people could put them in under a tree or next to a fence. So we've got to very carefully quality control those, but we're doing those on the fly as we're ingesting the data. What I wanted to show on here was the radar and satellite imagery. So if I zoom out, that layer should just load up now. We're also ingesting then the geospatial imagery. Radar here is the green, okay, and satellite data as well. So there's a mixture of point-based observations and then gridded data sets as well. A lot of remote sensing for satellite-derived observations can fill in the gaps where, as you can see, for example, offshore here to the west of the British Isles, where there's no weather observations. And out here, we are very, very much reliant upon the remote sensing inputs to the models. Also, radio sondes as well. I think if I go back to my chart here, here's a picture of a radio sonde release. So these are balloons that we released. There's about 800 radio sondes throughout the stations across the globe, and they normally twice a day will release a balloon that goes up through the atmosphere, sampling the atmospheric variables up through a vertical ascent. Okay, and those are then fed into the model. It's those vertical views of the weather profile, as you can imagine, from the vertical grid to build up that picture there, provide a crucial input into the chance of you getting your initialization right. Okay, so data assimilation, a critical part of the forecasting methodology. Hi, someone's at my front door. Sorry. Okay, so IBM have got a multi-model forecasting methodology. We do models all through, we work with many different weather models. We work with national Met agencies. The Met Office in the UK, for example, we use their weather model. There's agencies, the ECMWF are based in Reading. They run an ensemble model. They run their model 50 different times, and that allows us to, so we're putting in all these different data, and that gives us the best chance of seeing where the weather's the weather, what's the weather going to happen. So here we can see this is a tropical storm moving, or due to move east across across Mexico. And we can see the cone, this cone track here, this red area here is showing where the path is expected to go. Two of the models actually we've got actually outside of the cone track. Most of the models are going down the center of the cone track. So what IBM do, we pull in multiple models, up to about 100 we're using in our single forecast that you see in your weather map. We're pulling in the models around the clock as they're released by the different Met agencies. We verify and sort of assess how well the models are performing on a regular basis, and then these are weighted. And this weighted forecast gives us, on average, globally, the best chance of getting it right. Okay, and we don't always get it right. It's still the weather, but by looking at multiple models, you've got the best chance of getting the most accurate forecast. Okay. Machine learning, big buzzword, but it is effectively what's happening. So the weighting of those models is using machine learning techniques, and ultimately this is what gives us the best chance of getting the forecast right. We've got on the top here, FOD is what effectively is in your phone forecast. That's a single forecast that is the best of all the models that we've ingested and assessed. And then the PFP stands for it's a probabilistic forecast output, and I'm going to come on to that. That gives not just a single forecast, but it gives the spread. It gives, like on that cone track, it gives the ability to see what's the worst case, what's the best case, what's the exceedance thresholds, and it's a statistical output, and can be very, very useful to help understand what's the actual threat of the weather in the future, and what decisions should I actually make. Here's a picture of a supercomputer. This is the ECMWF supercomputer. They're actually moving to Bologna in Italy, but this was just down the road from me in Reading for many, many years. And they've got racks and racks of servers. Oh, actually, sorry, I've gone ahead. I was going to show you the chance of rain. Let's go back to my, oops, there we go. Oops, sorry. How do I get onto, there we go. Let's put this probabilistic forecast. What is the chance of rain? Okay, so this is a probabilistic forecast. We've got, we surface the statistics behind our deterministic forecast via an API, and this this script here I've written is basically accessing the, it's called a prototypes method, and what you're pulling in, what you're looking at here are effectively 50 different forecasts of temperature for a specific location. We used to call these spaghetti charts in the olden days. You can see all these different lines here all plotted, and they do over time generally diverge. The red line, the thick red line in the middle is the mean of the 50 different forecasts. The blue line is the standard deviation. For anyone statistically minded, standard deviation gives an idea of the spread. Okay, so what we see is generally over time, the spread increases. This blue line generally goes up in a linear, generally over time, but it's not a linear increase. And this is where we can start to be a little bit clever about how we use these data. Because if we look for times, for example, there's sometimes when the models will converge upon a specific weather event. If you get high pressure building across Northern Europe, for example, the conditions become very stable, and you can get a very confident, a lot of the forecasts will converge upon this particular event, and we can get a lot of confidence in that event happening. And the standard deviation then will drop because you'll have less spread in the forecast. If we look, for example, here, this event here, this is 100 hours from the time the forecast was initialized. This event here, we're very uncertain. There's a relatively high standard deviation. And we can see, just looking at the eyeball of the lines here, a lot of spread in the lines. Whereas the overnight temperature is actually less standard deviation. So they're more bunched together. So we're actually more confident in the minimum temperature, 1, 2, 3, 4, 5, 6 days from now, than we are in the maximum temperature at that particular time. Now, you don't get that confidence in your in your standard forecast, but the probability of rain, if you're looking at the probability of rain on your forecast, and I know the BBC put on this forecast now, we have this in our weather app, the probability of rain is driven by these probabilistic forecasts, and it's showing what number of forecasts will be saying that it's going to rain tomorrow. Okay, so it's statistically based, and that's really what it means. It is confusing rather the public, I think, sometimes, but there's good science behind it, and hopefully you've understood that. I followed on here. I put these in a box and whisper chart and then coloured them in. You see here, the red is less. These are areas where we're less confident in the forecast than the green, which are where we're more confident in the forecast. So you can actually see the overnight temperature forecasts we're more confident in than the daytime maxima. Okay, let's go back to my slide again. Okay, so we've covered chance of rain, intelligent gridding. So let's have a quick look at the IBM weather model. This is a single deterministic model. So this was launched in its current format just over 2 years ago. So IBM have run its own weather model for many years. They worked with, for this model, they worked with National Center for Atmospheric Research, US meteorologists who created the, worked together on the physics. There's new physics in this model. And the exciting thing about this model is, well, first of all, it's in using some of the personal weather station data that we've, that I've shown already. So this crowdsourced data, which I think is really exciting. But it's the fact it's running on a 3-kilometer grid globally. Well, I say globally, and this is where this gridding, this sort of specialized gridding things is comes in. Just let me quickly. So yeah, I called it initially. I think on the invite it said dynamic gridding. I was in touch with one of the head of the chief scientist for atmospheric modeling. He said it's not actually the correct term, dynamic gridding. We actually would call it unstructured grid in 2 dimensions. And what this effectively is, if I just go on to the next slide, is it's actually a grid that they don't have the same grid size across the whole globe. Okay, so we can see in the bottom right hand corner here, they've got a 3-kilometer grid running over most of the populated areas, and then a 15-kilometer grid running over the ocean and also the Sahara Desert. And this allows them to get better value out of their computing resource. Okay, it's also, I think, some of the exciting technology behind this is blending together different runtimes of weather models. So we've got an hourly update for the short-term model, and then we've got 6 hourly updates for the medium term, and then we after 72 hours we're then moving more towards a blend of the different National Met Office models. Okay. What else? Okay, so yes, 2D unstructured mesh, not dynamic gridding. Okay, that's the key takeaway from that. But this is just really about managing your computing resource. Here's a picture of the supercomputer behind our model here, and it's running on GPUs. Please don't ask me huge amounts of details about the GPU structure, but it's about using the computing power more efficiently. Yeah, so if you think back to Fry Richardson, if he was going to have 64,000 mathematicians plugging away, you really want to put your mathematician resource in the areas to help forecast for the areas where the weather is going to have the greatest impact. Okay, and that's what we're effectively doing with this unstructured grid. Okay, actually, just go back another slide here. We look at the difference in resolution then. So this is I'll just play this little chart again. This is on the left is from the GFS model from a few years ago. And this is, you can see already, just even eyeballing this to the consumer, the difference in granularity of the high resolution output for this model. You can pick out features here and the shower development coming across India. It's by putting and better managing your computing resource and getting that grid size down, you're able to get more accurate more accurate outputs. Okay. Right. I'm going to come to my final notes. Right. So short-term modeling versus climate modeling. This image here on the right, we can see is taken from a data repository that we have called Pairs Geoscope, and this is just showing some of the climatological data sets we have on there. And this is effectively one of the main differences between climate modeling versus weather modeling. Weather modeling is really focused upon short term. So from sort of now up to, I mean, our models run up to 15 days ahead. Some can run them longer, but really it's about giving people the weather, the atmospheric change over short term. Climate modeling is when you move further ahead, and they are effectively an extension of weather modeling. But whereas we're looking short-term, short time spans, and also potentially specific areas for weather models, climate models tend to be broader and analyze over longer time spans. And they also can include things like ocean circulation, melting glaciers, things like those, which also do, feed to things like the El Nino, things like ENSO, which are some of the statistical descriptors behind what's happening on the planet as a whole. They do require a slightly different computing approach because, for example, they can be run over longer timescales. They don't need an hourly update. You don't need your climate model to be updating every hour. So they do tend to work with the computing technology slightly differently. And also the other key difference, I think, is that they are still very heavily linked to statistical inputs and also statistical outputs. So the IBM research team in the UK, they're looking in their climate model to include the historical climatological data and how that was impacted in the past to then forecast not just the weather itself or the climate itself, but actually the impact of the weather on humans. So it's things like what's going to be the flood impact of the weather in the future. Okay. I've got another slide here. So I got this slide from the IBM research team, and this is the IBM's one of IBM's approaches to regional and local climate modeling. And we can see here, I mean, there's various different ways of structuring this. The outputs tend to be led towards the impact. Okay, and this is really where one of the major differences is, and it becomes, I'd say, in many ways less well defined because some people are more interested in the impact of climate and climate change on their operations rather than just the climate themselves. Okay. I think that's my last slide. I was going to give a plug to this. This is an interesting paper. I'll put this in the chat actually from my colleague Lloyd Trenish, and he's done some great research into this. So IBM are doing a lot of really interesting work in the climate modeling side of things. And I do suggest actually, Martin, this one for us is to get them on to explain some of the technology behind this, because this is really exciting stuff, and I'm sure relevant for some of your members. Okay, I'm done now. I think I've raced through in 29 minutes, it says. So let's have a look at questions. Shall I?
Time to perfection. So we've had.
I did go on a Royal Navy training course before I was allowed to work in the offshore industry, and they hammered into me, you deliver your weather briefings absolutely on time, and that's one thing I've always taken away. So yeah, hopefully that's
the training is shining. The training is shining through. We've had one question from Paula in the question and answer session about how is the data ingested. Now I think I took a note. This I think popped up at the time you were talking about data assimilation and quality control. So towards the beginning of your talk, I think sort of chapter 2.
Yeah, well, perhaps I'll just flesh that out a bit. The ingestion is super complex. I mean, I understand that's one of the reasons why IBM bought the weather company 6 years ago. They really wanted to get their hands on the computing. It was all cloud-based data ingestion of the weather data, and they've used that technology in other areas, because we're pulling in I mean, my weather station in my garden updates every minute, and we're pulling in, 250,000 personal weather station observations around the clock. We're pulling in all of the airport, all of the radio sons, and then of course you've got into that. You're also adding in satellite and data feeds as well. And that data assimilation is, I'd sort of argue, possibly the crux of any weather modeling agency. Now we do that, but also the Met Office, the other national Met agencies are doing that as well. I think our approach is slightly different because we are commercial as a commercial weather agency. So we tend to pull in the freely available weather data, which is generally from the National Met Services, but we then also try and improve that by adding in extra data. So there was work underway to look at the pressure sensors in smartphones and things like that, I think, which is really exciting. I think they found a lot of trouble because, of course, no smartphones are calibrated. So you take a pressure reading from a smartphone, but if you go up and down in a lift in your building, you'll see that the pressure will actually drop as you go up in the lift, and that could trigger off a cyclone warning potentially. But they can do smart things with that data, and I think that's why IBM are very well positioned to try and sort of push the research on that. But yeah, data assimilation is absolutely critical, and building that picture, that initialization picture to put into your model is the crucial first step, because once you've got that on as tight a grid as possible, you're then giving yourself the best chance of projecting that forward using the equations that I flashed up on the screen. Please don't ask me any questions about those.
Wonderful. And we've had another question in from Rowan. How often are models, not data, updated and or new models introduced?
Yeah, so that's a good question. So the IBM model, as we've seen, runs parts of it on an hourly basis, and then those are integrated with a 6-hourly model run. And those themselves are continually ingested and blended with the models from the National Met Services that we're pulling in. So, and the National Met Services, these global models tend to be on generally about 6-hourly model run. Some of them are 12-hourly. So, and that time is really the time it takes to pull your model data in, initialize the model, and then leave it running. And then also, so that's maybe takes 5 hours, and then you've got another hour to then sort out and project and surface those data to various displays to feed the data into other models, for example. But yeah, the timiness of it all is super complex, and the IBM forecast. So if you look at your phone and refresh that updates every 15 minutes. And what that does is it takes the latest data available. So it will take for example, the ECMWF, I showed their supercomputer. It will take their model data as soon as it's available, and give a large portion of the ECMWF data in our sort of mid-range forecast. But then as soon as another model comes in, it will consider that as well. So it's this dynamic, what I think I've said, it's using AI to kind of try and blend the models together. That gets really, really exciting. But climate model wise, a climate model you can leave that running for weeks and weeks and weeks, because it's not so critical with the delivery time. And this is where the two parts of the science kind of diverge, because climate models tend to have a lot more time to think about their outputs, and getting that requirement is very, very different. But yeah, really good question, Ryan.
Good. Well, we've got a really good one here from Aloysius Dempsey. Is the absorption reflection of sunlight from clouds still a major piece of forecasting uncertainty in modeling, or do you have a handle on it via observations or via algorithms now?
Let's have a look then. Is the absorption? Yeah. Okay, so we've done a lot of work with satellite data, actually. Not necessarily. I work some of the products I've shown. I work with a thing called Environmental Intelligence Suite, which has been actually just relaunched this week. And within there, we have a lot of satellite imagery. And I know some of the problems of satellite imagery are reflections and not being able to see through clouds as well. Now, the science of remote sensing is generally improving. There's a lot more satellites in space, and they are getting better. but there's still obviously certain there are limitations with clouds. That's not going to go away. I'm seeing the improvements in that hardware are improving, so we're going to still get improvements. Actually, just thinking back to, sorry, I'm going. Oh, yeah, no, but it is improving. I think this is the exciting thing about being a meteorologist. There's so many different aspects to the science and things. So hardware improves. That's going to give us a better improvement. One of the talk about satellite information. One of the things I've seen that's improved, that's being fed into forecasts now, is communications between satellites, because they have to travel through the atmosphere. They're able to use the time lapse it takes for one satellite to transfer to another through the upper atmosphere. They're able to use that to derive upper air, information about the upper air. It's generally the upper air, the upper atmosphere, which causes, which is what we're looking for. So that's why it's back to radio sondes. The radio sondes releases, there's 800 of them, I think I said. Those provide critical information to initialize the models with, because if you don't know what the upper atmosphere is doing, things like modeling, frontal passage, because fronts, obviously, a weather front will go up, tens of miles up through the atmosphere. You need to have a picture of that weather front through that sort of the vertical ascent is critical in initializing your model. And if you've got a radio sonde, the vertical ascent through that weather front, you can build up a picture of how well progressed that is, and that gives you then the chance of better forecasting. Actually, on radio sondes, I was always told to rely on the midnight and the midday initializations for the weather models, was told to be better than the 6 o'clock runs, because they would include radio sonde data in their initialization. I think with better developments in satellite derived upper air data, that's less so now. But yeah, it's little things like that that we're that feed into what we as meteorologists try and use.
So we've had the excellent answer. We had another question from Jonathan. And what business benefit does IBM as a business derive from forecasting the weather?
It's a good question. It's helping customers. It's helping our end users. And we put a lot of science and technology and resource into producing our forecasts. I'm proud to be part of that team, or sort of certainly on the periphery of that team. And then I'm also really pleased to use that technology to help make a change. And the accuracy stats, the accuracy reports that come out show that our forecasts do very, very well globally. If you Google for the accuracy stats of IBM's weather, yeah, we do very well globally. And we want to, I try and make sure I can take that to my customers so they can be using the most accurate. There's a lot of free weather data out there. I built a weather website years ago based on free weather data that I found, and that was okay. Was it the most accurate? No. I think for business now to make decisions with the weather, please, try and start off to give yourself the best chance of making the best decisions. And that's what, I work with insurance companies, a Formula One racing team, they have to make some very important decisions based on the weather. And for them, the criticality and the accuracy is extremely important. So the benefit is potentially very, very high. Yeah, so good question.
We've had another one in from Paul. I think it's meteorological observations and radar data are fundamentally different.
Yeah.
How do you assimilate these?
It's, from what I understand, the point-based observations, they have to be put onto a grid. And this is the correct. So radar, you're basically getting a raster data set. You're getting a gridded view of what the radar imagery is, and obviously satellite imagery as well is on a raster data. Combining that with point-based observations is difficult. The point-based observations will not be at your grid point. You've got a 3-kilometer grid that we're initializing our model with. It's very, very unlikely that you'll have a point-based observation at that a surface-based point observation at that particular grid point. So you need to interpolate, and it's that interpolation ultimately that's adding errors and a bit of errors into the and adding inaccuracy into the observation network. And this is where ultimately, I think I've mentioned some of the problems with forecasting. This is where we ultimately this inaccuracy in building up a view of the weather does fall down, and this is where ultimately, after a certain time, models diverge, and you get the inaccuracy in the forecast. I worked as an operational forecaster for 8 years. My first 2 years, because I studied physics originally, and I liked from the meteorological science, I like the accuracy. I like the fact you've got some equations to describe it all. It still took me years to get around with the fact that ultimately the forecasts will be inaccurate. You will never get it completely right. And unless you had a weather observation at every meter on Earth, you would never build up that perfect picture of what the weather is doing at every point on Earth. Now we try and improve that. We try and sample and fill in the gaps between observation stations. But as you can see from the maps I've shown today, there's some big old gaps out there, and we're just never going to fill in the gaps there. And that really impacts how we, the accuracy of the forecasts that we've got. Yeah.
Excellent.
I keep on answering other questions, the one that have been asked, but
oh, well, it's wonderful. You've been brilliant. I mean, I think we're all in for questions, and I think we're pretty much out of time. So the question is, of course, will we get a white Christmas? Can you answer us that?
Oh, that's the premium service. So yeah, I'll actually hang on. Has there been any significant changes in the underlying algorithms? So I'd like to comment on that. Actually, that's a really good question, and this is where it's often done with academic science. I think you saw the IBM model that we've redone was done in conjunction with NCAR. So we do rely on a lot and work very closely with academic institutions, and they're people who are coming up with new physics, with new physical parameterization schemes. The fundamental equations themselves, though, are not changing. And this is why it excites me so much. It's as a branch of science, the fact that those equations I showed, that does form the basis of a lot of these models. Yeah, as technology improves, as science improves, moves on, it is getting better. One of the things I'm seeing more and more, I think, is statistical outputs and inputs as well. And I think statistical modeling, using statistics, and then of course with that you're able to adopt these kind of machine learning methodologies as well. I think that's where the science is going these days, and that's why it's quite exciting being part of IBM, because IBM are applying some of their computing science to improving the meteorology as well. But yeah, that's a good questions from Aloysius. Nice to meet you. Thank you for that. Right, sorry, Martin.
I think we're done. Your military trainers will be looking at their watches. I think you've got about a minute left. So I think it's
please follow up with me find me on LinkedIn, and I'm happy to talk and explore more, and hopefully I've given a bit of enthusiasm. I can also connect people with, I don't know it all by all means, but within the IBM network, I can probably connect with people who want to dive deeper. The climatological stuff, I think, is something I'd be particularly interested in following up with people. So please go and speak to me about that, and I can put you in touch with the right people there as well. So yeah, thanks.
Wonderful. Well, thank you very much, and thank you from everyone at BCS and all our participants. So thank you very much. Cheers.
Thanks very much. Cheers, guys.